All right, guys, welcome to async number 2 for statistics. We're going to pick off where we left off with the binomial theorem, and then we're going to go into a little bit of the study of permutations. So the binomial theorem is something you did way back when in geometry, not geometry, what's that class? Pre-calculus, in the single periods. And for those of you who have Mr. Strandberg, I know you have really good notes on this. And for those of you who didn't have Mr. Strandberg, well, go steal someone who had Mr. Strandberg's notes. But this is another use for the binomial coefficients. All right, this is another use for the binomial coefficients. And the binomial theorem says x plus y to the kth power, right? First off, it's not x to the k plus y to the k, right? This is not true. This is what some math people call the freshman's fallacy, or the freshman dream, right? We wish this was we wish this was true, but it's not. But what is true is that this is equal to, now, what's important is we have this kth power, so it's going to be k choose 0, and we're going to have x to the k minus 0, y to the 0. Then it's going to be k choose 1, x to the k minus 1, y to the 1, plus k choose 2, x to the k minus 2, y to the 2, plus k choose 3, x to the k minus 3, y to the 3, and so on until the last one is k choose k, x to the k minus k, y to the k. Okay? All right, so this is the formula for x plus y to the k, and we do a little simplification. K minus 0 is just k, and k minus k is just 0. Right, so this is the formula, and if you're good at summation notation, we could write this. We talked a little about this the other day. The sum I equals 0 all the way up to k. K choose I, x to the k minus I, y to the I. Right, so these two are the same expression, just written in two different ways. And you could use either one of them for your binomial theorem. And of course, this is weird. This is like hard and abstract and everything. But if you see a couple examples, it'll make a little more sense. So let's do x plus y to the 5th. All right, x plus y to the 5th. Let me make my pen a little thinner. X plus y to the 5th. So this is going to be 5 choose 0, x to the 5th, y to the 0, plus 5 choose 1, x to the 4, y to the 1, plus 5 choose 2, x to the 3, y to the 2, plus 5 choose 3, x squared, y cubed, plus 5 choose 4, x to the 1st, y to the 4th, plus 5 choose 5, x to the 0, y to the 5th. And I'm going to make this just a bit smaller because we're going to simplify, which is then equal to, zoom in even more, 5 choose 0 is 1. So this is 1 times x to the 5th times 1. So this is x to the 5th plus 5 x to the 4th y plus 10 x cubed y squared plus 10 x squared y cubed plus 5 x y to the fourth plus 1 y to the fifth. So there's a final answer. So annoying, yes. Hard, not particularly, right? If we just go through these steps, we will be okay. So let's now look at number 2. Okay? Number 2. 2x plus 3. Not number 2. I don't want to do number 2. I actually want to do number 3. Because number 3 is where it gets a little bit trickier. Because it's got this minus sign. Okay? So here's what I want you to do. If you have something like this, if you ever have a minus sign, what we're going to do is we're going to do like this. We're going to take this, make it a plus sign, and we're going to make this negative 3y. Okay? And once we do that, we follow the same pattern. We go to the fifth power here again. So we're going to have 5 choose 0, x to the, 5 choose 0, x to the fifth minus 3y to 0, right? So now that whole thing becomes the y for the new problem. Plus 5 choose 1, x to the fourth minus 3y to the first, plus 5 choose 2, x to the third minus 3y squared, plus 5 choose 3, x squared minus 3y cubed, plus 5 choose 4, x to the first minus 3y to the fourth, and plus 5 choose 5, x to the 0 minus 3y to the fifth. Now if we simplify all this, again, this is 1 x to the fifth times 1, so this is x to the fifth. But then I have plus this, let me do a different color. This guy's equal to 5, and this guy's equal to negative 3y. So if I have 5 times negative 3, that's plus negative 15 x to the fourth y. So the issue with the minus signs is we get some negatives floating around. That's not a big deal, right? 5 choose 2, that's 10. Oops, I don't want to do it like that. This is 10. And this is positive 9y squared. So I got 10 times 9 is 90. So this is 90 x cubed y squared. Over here, 5 choose 3, this is again 10. And this is minus 27y cubed. So this is plus negative 270 x squared y cubed. This guy's 5. This is 81y. So this is plus 5 times 81. That's 5 times 81. 5 times 80 is 400. So 5 times 81 is 405. So this is 405 x y to the fourth. This is 1. This is 81 times 3 is 243. So this is negative 243y to the fifth. So we have plus negative 243. X to the 0 is 1, y to the fifth. All right, so hopefully that brings back some memories. And how can we make this a little easier? Well, we can use Pascal's Triangle. Now, I know a bunch of you were groaning when I said Pascal's Triangle. but we'll be okay. What's important to remember is that it's just an easy way to calculate the binomial coefficients. So if you remember Pascal's triangle, it kind of looks like this. It's 1, 1, 1, 1, 2, 1, 1, 3, 3, 1, 1, 4, 6, 4, 1, 1, 5, 10, 10, 5, 1. And if I want to start making the next row, well, I'm going to put a 1 on the end. I'll put a 1 on the end. And to make the next row, I'm going to add these two numbers together and put it right here. So 1 plus 5 is 6. 5 plus 10 is 15. 10 plus 10 is 20. 10 plus 5 is 15. And 1 and 5 is 6. And we always end with a 1, right? So this is the next row. Next row of Pascal's triangle. All right, but how does this make this easier? Well, it just takes a little bit of weird note keeping. We count this first row as the 0 row. So this is the 0 row. This is the first row. This is the second row, third row, fourth row, fifth row, sixth row. And remember, Pascal's triangle goes on forever. So these rows go on forever. How do you know you're in the right row? Well, the 0th row is a little hard. The first row is a little hard. But the second row is going to have a 2 in the second place. The third row is going to have a 3, a 4, a 5, a 6. And really, the first row has a 1 in that place, too. So if you look down this diagonal, it tells you what row you're in. And why is this helpful? Well, since we're in the 0th row, this top entry is, let me do it in a different color. It's a little easier to see. This top entry is 0, choose 0. Then the second row, the first row, we have 1, choose 0, 1, choose 1. The row, it's a bad color, the row we are in is the top number in the binomial coefficient. So we're going to have 2, choose 0, 2, choose 1, 2, choose 2. 3, choose 0, 3, choose 1, 3, choose 2, 3, choose 3. And each row, I start at 0, and I end up at the number of the row I'm in. So in the 4th row, I'm going to start at 4, choose 0. Then I'm going to get 4, choose 1, 4, choose 2, 4, choose 3. And I know to stop at 4, choose 4 when these two numbers are the same. And this goes on forever, too. But this is a way to organize yourself when you're trying to figure out Pascal's triangle. If I want to know what 4, choose 3 is, well, I count, let me get a different color. I could do it in that color. I count 0, 1, 2, 3, 4. So this tells me we're at the 4, and then I got to choose 3. So, oops. 0, oops. 0, 1, 2, 3, 4. And then once I get here, I want to do 4, choose 3. You're going to count 0, 1, 2, 3. And 4, choose 3 is indeed 4. Just a different way of calculating your binomial coefficients. Now, there's a lot of cool patterns in Pascal's triangle, which we can chat about if you ever have free time, but it's not necessarily important for our course. All right, and the last thing we want to talk about today is a permutation. So we talked about combinations, and now we want to talk about permutations. And ordering, definition 1, an ordering or a rearrangement of the numbers 1, 2, blah, 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 all the way up to n, is any way of listing the numbers so that they all appear exactly once. So let's talk about, for instance, if I take the numbers 1, 2, and 3, how many ways are there to rearrange them? Well, it's a listing of the numbers so in any order so that they appear exactly once. So I can do this, I can do this. 2, 1, 3, 2, 3, 1. 3, 1, 2, 3, 2, 1. And these are all the rearrangements of this initial guy, of this initial list. right? So there are actually 6, right? Because the rearrangement of doing nothing actually counts, right? So we're doing a lot of nothing in this class so far. But every time we do nothing, it counts for something. So, right, there are 6 rearrangements of the numbers 1, 2, and 3. And sometimes we also call a rearrangement a permutation. Right? Now, permutation is kind of a loaded word in math. It means a lot of things, sometimes things way more significant than just a rearrangement. So I try to stay away from that word sometimes. But an ordering or a rearrangement is definitely the right word for this. And then permutations, maybe a slightly fancier word. So look at theorem 2. There are n factorial rearrangements of the set 1 through n. Well, that makes sense, right? That makes sense. Let's think about it. In this example up here, there was 3 numbers to rearrange. There was 1, 2, and 3. And what is 3 factorial? 3 factorial is equal to 3 times 2, which is indeed 6. So there are 6 rearrangements of the numbers 1 through 3. It's a theorem. We're not going to try to prove it. But theorem 3 we're actually going to talk about. So we have this weird new notation. This is a permutation notation. Now there are npk, which is n factorial over n minus k factorial ways of choosing a subset of size k of a set of size n and then rearranging the subset. That should say subset. Subset. Okay? So now, let's talk about why this has to be true. All right? Because there's something in here that we looked at last time. Ways of choosing a subset of size k from a set of size n. Right? We know how to do that, don't we? The number of ways to do that, if I want to do that orange fact right there, it's n factorial, k factorial, and minus k factorial, right? This orange thing, this is n choose k, right? But then I want to rearrange the subset. And how many ways are there to rearrange a subset? Well, the subset itself, we got to care about how many numbers are in it, right? How many numbers are in it. And well, we're choosing a subset of size k and then rearranging it. So there are k elements in it. K elements. So if there are k elements in it, how many ways are there to rearrange k elements? Well, there's k factorial ways to rearrange them. And if you remember what we talked about today, if we're counting kind of 2 things that happen at the same time, we're choosing something and then arranging it, we multiply. If we multiply these 2 things out, this k factorial and this k factorial, you now can't see the other one. Try a different color. How about green? This k factorial and this k factorial will cancel, leaving us with n factorial n minus k factorial, which is exactly what we have up here. Ding, 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 ding. This is p and k. All right? So this is the reason why that formula works based on the choose formula. Okay? Now there is something to be careful here. There's something to be very careful with this. This is k. This is n minus k. Don't accidentally put k in the denominator. You're not going to get the right answer. Okay? You won't get the right answer. All right, so now let's do some examples. it seems as if the rest of my problems didn't get sent over here. So let's do maybe two kind of simple examples. One, so let's say, how many ways can there be a race with 7 people? Race with 7 people, and I want to give out a gold, silver, and bronze medal. All right. So at this point, you're gonna have some extra problems to do after this. So if you just want to listen to this, you don't not take the notes down. That's fine. So how do I do this? Well, gold, gold. Wow, gold, silver, and bronze. Right? Those are all different from each other. Those are all different. Winning a gold medal is different than winning a silver, is different than winning a bronze. So the order matters here. So let's think about what we're doing. I'm giving you 7 people, and I'm asking you to put 3 of them in order. Right? So in other words, this is 7p3, which is 7 factorial over, not 3 factorial, but 4 factorial. Right? 7 minus 3 factorial. 7 times 6 times 5, which is what, 210. Right, so there are 210 ways to give out a gold, silver, and bronze medal, unless Usain Bolt's winning, and then we know he wins gold. But that's a stupid joke for a different day. Okay? And now there's one more kind of thing I want to think about, and then I'll set you loose on the problems. Set you loose on the problems after this, too. Let's assume I have 6 men and 5 women, and I want to sit them in a row. Sit in a row, so that no 2 women sit next to each other. Right, so that no 2 women sit next to each other. So we got to kind of think about this, right? So this isn't just a straight permutation. It has to do, there's a restriction on it, right? So we got to think about this restriction. I got to sit 6 men and 5 women in a row, and I need it to be the case. So I need 11 seats, right? I need 11 seats. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 seats. 11 seats. Okay? And if we think about it, how can I sit everyone? Well, if I start with a man, well, what can I do with the women? If I put another man here, let's say maybe I'll put a woman here. I'll put a man and then a woman, and a man and then a woman, a man and then a woman, and then a man and a woman. Did I get it? Did I get enough? So I got 1, 2, 3, 4, 5 women. I have 1, 2, 3, 4, 5, 6 men. So this way it works. I can start man, man. Right? I can start man, man. Can I start? Well, perhaps this question is a little, let me rephrase this question. Because this doesn't really match the one in the notes. Right? So I want no women sit next to each other and no men either, right? So no one of the same gender sits next to someone else of the same gender. So again, we have 11 seats. We have 11 seats. If I put a man in the first seat, well then I have to put a woman in the second seat, and I have to put a man, woman, man, woman, man, woman, man, woman, man. And I end up with 6 men and 5 women. Right? So what do we do? How many ways can I count this? This is the only way I can do it. This is the only way I can do it. But how many ways are there to count this? Well, essentially what happens is the men and women are kind of stuck in place, right? Like I must have a man in the first seat. I must have a man in the third. I must have a man in the fifth, right? 7th, 9th, 11th. So all we have to do actually is count how many ways there are to rearrange the guys in these seats. And how many ways are there to do it? Well, I have to arrange the 6 men. Oh, well, there's 6 factorial ways to do it. Right? And then I have to rearrange the 5 women. Like I know they're already in these seats. I just have to know what order I'm going to put them in these seats. I have to rearrange them. So that is 5 factorial. So it's going to be 6 factorial times 5 factorial. And there's the answer to the problem. So for your async work, you're going to do any problem in the note sheet that we didn't do and turn it into me by 7. Good luck.